All right. So as we just discussed, this is going to be a quick review over weeks 1 through 4. And I even threw a little bit of week 5 in there kind of towards the end. So that way we can see how some of the stuff we're talking about becomes applicable in week 5. And then we'll expand upon that when we get to week 6. So all the way back at the beginning, the very basics, overview of statistics. What is statistics? Data, population, and sample. Just making sure we understand the definitions is a pretty key part of the class. So statistics is the overall science of collecting, organizing, analyzing, and interpreting data in order for us to make decisions. So that's the concept of statistics. We collect data, we organize it in whatever fashion, we analyze it by doing things like calculating means, medians, modes, standard deviations, making graphs, and then we interpret it. That's kind of the confidence interval as well as the hypothesis test piece in order to make decisions going forward. And data is just any information we can collect. So anything I can observe, record, count, measure, anything like that can be considered data. So the concept is we take that information, we combine it, we do statistical analysis on it, and we end up coming up with conclusions, and we're able to make decisions based on those conclusions. Now, population versus sample is a pretty big concept in stats. Population represents the collection of all possible outcomes of interest. All possible outcomes of interest. So if I'm looking at students at Arizona College, my population would be all students that attend Arizona College. And that would probably be across campuses, things like that. A sample is a subset of that. So if my population were all students across all campuses that attended Arizona College, a sample could be the Las Vegas campus. That's a subset or part of that population. So it's very important for us to understand what our population is, because that's what we are trying to make inferences on. So we don't want to go out either collecting samples that aren't representative of the population or making conclusions about a population that's not what we think it happens to be. So those are some of the key definitions we see right there in statistics. Other ones, parameter and statistic. Parameter is a numerical description of a population characteristic. Think of that as the population mean or the population standard deviation. Those are parameters. Anything that describes a population. A statistic is a numerical description of a sample, right? So that would be the sample mean, the sample standard deviation. Those would be statistics. So parameter and statistics are effectively the same quantities, just expressed with a population versus a sample. And so at the end of the day, we use statistics, sample statistics, to estimate population parameters. And that was the concept we've done so far with confidence intervals. We collected some data, we had a sample, we constructed a prediction or our best guess as to what the population mean was, which is a parameter. So statistics estimate parameters. And then just statistics is broken up into two main branches. Weeks 1 and 2 were really descriptive statistics. Organization, summarization, display. Things like computing the mean, median, mode, standard deviation, range, graphical summaries. Those are all descriptive statistics. Inferential statistics is when we start making decisions based on information that uses basically probability as its underlying assessment. So everything we've been doing with the normal distribution, computing the Z and the T values, finding probabilities, areas under the curve, and now confidence intervals, those are all in the realm of inferential statistics. We can take that information and make decisions about it. So that's the concept there. Anyone have any questions yet? I'm hopeful those definitions are becoming more second nature. All right, couple of things, right? So some things that we're going to need to be able to calculate going forward, or at least understand what we're dealing with. First thing is we're going to need to compute means from data sets. We've had to do that in a couple of discussion posts. Shouldn't be that hard for us to calculate a mean. Those are pretty easy to do by hand as well. It just can be time consuming if we have a lot of data. So the mean is calculated as X bar, or your book might actually use capital M to represent the mean, is the sum of the X values over N, where N is my sample size or population size. So sum of the X means add up all the values divided by the total number of values. Once we have the mean, we can then compute the population variance, sigma squared, as the sum of the X minus mu quantity squared all over N, where N is the size of the population. And then the standard deviation is always just the square root of the variance. So, key things to know from here. Population variance is represented by sigma squared, and the population standard deviation is represented by sigma. We want to know what those symbols are and what they mean, so that way when we see them going forward, we know how to deal with them. And then the relationship between standard deviation and variance. The variance is the standard deviation squared, and the standard deviation is the square root of the variance. So there's a square root relationship between those two. Once we're dealing with a sample, the big difference is instead of dividing by n, I'm going to divide by n minus 1. We lose a degree of freedom because we're estimating X bar instead of knowing what mu is. So because we have an estimate there, we have some level of error in our assessment, which causes us to lose a degree of freedom. So the sample variance, very similar to the population variance, we divide by n minus 1. Sample standard deviation is just the square root of the sample variance. And the key here, sample variance, the symbol is S squared. Sample standard deviation, the symbol is S. Same relationship between standard deviation and variance. The biggest deal is, are we dealing with a population or are we dealing with a sample? Okay, so suppose we had a problem that looks something like this. Find the mean and standard deviation of the following data set. And we're given all these numbers right. Right, first thing we might want to do is go, okay, there's a lot of data right there. I want to find the mean and standard deviation. The mean's probably not hard for us to find, but that standard deviation may be a little bit challenging for us to find. So instead of sitting here and trying to do any of this by hand, and this is going to become relevant when we're dealing with more confidence interval problems, more hypothesis testing problems, is we're going to have to take that information and we are going to have to go do some assessments to determine whether or not the data that we happen to see is statistically significant. So what we want to do is we want to come find some kind of descriptive statistics calculator. This should be the one that I gave y'all during your week 1 discussion post for you to use. And so we end up pulling out the information, and then we're going to take a look and say, okay, what is my mean? What is my standard deviation? So I just copied that data, and I'm just going to paste it in right here. Got it all here. And then I just need to know, am I dealing with a sample or am I dealing with a population? The thing that's going to be most different is that standard deviation and variance value. So suppose I'm dealing with a sample. I click calculate. It tells me that the mean's 11.06 and the standard deviation for the sample is 7.09. Gives me a bunch of other information here that could be useful to us. We can just see it. It kind of gives you some information over here about all of these different calculations and how they're done and what they represent. So that's good information for us to have. So I want y'all to be using this when you're doing your assignments. Don't go wait and do a bunch of other stuff. If we happen to need a population, or we're taking a look at a population, I'm going to compute the same thing, and note that the mean has stayed the same. They just changed the symbol. And the standard deviation is different in calculation and different in symbol. Well, so I just need to determine which one I have, which one do I want to take a look at. Demi, so that's the thing. If you are going to be doing the calculations manually, what's going to end up happening is you're going to have to be a little bit careful with rounding. You definitely don't want to round in the middle. As you can see that the mean doesn't work out to be a very nice number. So doing the standard deviation by hand is going to give you a bunch of different things. And if we keep rounding in the middle, our value may end up being off by 1 or 2 points when it comes to standard deviation. And that could be a significant amount, especially in our conclusions going forward. So when we get to the very end of the problem, that's the point in time that we can round. And I usually like to round things to about 2 decimal places. That makes sure significant things aren't going to change if you round to 2 decimal places. Kaylee, we will never need to calculate the standard deviation on an exam by hand. It will either be given to you, especially at this point in class, or it'll be more of a conceptual question. And the conceptual question might be something like which data set has a bigger standard deviation, or what things impact the standard deviation, things like that. All right, any questions about using this descriptive statistic calculator or anything we've covered so far? Okay, so let's get back to the slideshow and we'll continue going on talking about other things. All right, standardizing scores. So as y'all have seen in week 3, week 4, we started talking about standardizing scores and we computed the z-score. So what the z-score really represents to us is how many standard deviations away a specific value in a data set falls from the mean of that data set. So for example, if the exam average on our final exam happens to be a 70% and the standard deviation is 10, well, then anything that is 1 standard deviation away would be at least 10 points from the mean. So a score of 80 would be 1 standard deviation from the mean because standard deviation is 10. I add 10 to 70, I get to 80. So this just tells me how many standard deviations away from the mean is the data point that I happen to be looking at. And then we note that z-scores that are greater than 2 may be deemed unusual and should be further investigated. So anything that's 2 standard deviations away from the mean or greater may be concerning to us. And that's going to come up, we'll talk about it in a few slides there. But that really comes up to how much, what percent of the data happens to fall within 2 standard deviations of the mean. So now we're going to walk through just a basic problem that takes a look at calculating a z-score. So, change this from bottle. Soda fill volume follows a normal distribution with a mean of 12 ounces and a standard deviation of 0.5 ounces. Find the z-score if we measure a single bottle to be 12.4 ounces. So I see that my soda fill volume follows a normal distribution. I want to compute a z-score. My equation would be x minus mu divided by sigma. So now I just need to identify which values are which. X represents my measurement value. Mu is the population mean. Sigma is the population standard deviation. So my measurement value was 12.4. My population mean, this comes from a normal distribution with a mean of 12 ounces, so that's going to be 12. And the population standard deviation, it comes from a normal distribution with a standard deviation of 0.5. So from this point, I just do the math. 12.4 minus 12 is 0.4 divided by 0.5, which gives me 0.8. So the z-score for a measure of 12.4 is 0.8. What that means is that a measurement of 12.4 ounces falls 0.8 standard deviations above the mean. If my z-score is positive, that means it falls above the mean. If my z-score is negative, that means it falls below the mean. So as we can see, 12.4 is greater than 12, should fall above the mean, and it's not quite a full standard deviation, 0.8 standard deviations. Questions on that? All right. Now, transforming a z-score to an x value. So just like we transformed, just like in the previous one, right? We took a measurement value, we transformed it into a z-score. I can kind of work myself backwards by taking that equation and solving for x. X equals mu plus z sigma. And then I can try and figure out how many, based on the number of standard deviations away, what measurement value do I need to take a look at? So let's take an example. So exam scores follow a normal distribution with a mean of 70 and a standard deviation of 12. Which exam score represents the 90th percentile of exam scores? All right, so now we are going to go into something a little bit deeper. Something a little bit deeper. And before I go there, let's change this up a little bit, or let's hold off on this this problem right here. And we're going to change it up just a touch for now. Which exam represents a z-score of 1.5? Let's do that. We'll come talk about this one later. So if I'm trying to find a specific measurement based on a z-score, I basically just take my z-score, solve it for x, and I'm given this equation right here. So then all I do is I just plug in the information that I have. Normal distribution with a mean of 70, so mu is 70. Standard deviation, that sigma is 12. Z-score is 1.5. So then I get 1.5 times 12. So I'm going to do that math. 1.5 times 12 is 18, plus 70 gives me a score of 8. So we end up with a score of 88 represents a z-score of 1.5. All right, questions on that? We will come back to this example again, and we'll answer this one right here. But we need to make sure we cover one little topic. All right. So now we're going to start talking about the normal distribution. So the normal distribution is a distribution we're going to be dealing a lot with. That one, the t-distribution, and then we'll actually learn a third one as we continue on. But the normal distribution is also known as the Gaussian distribution, is a probability density function is what they call it. And it gives me a situation where it has a single peak, it's bell-shaped and symmetric, and the mean, median, and mode are all equal. Got that one little peak right there. Total area under the curve is equal to 1. We use this information all the time. The area under the curve is equal to 1, and we use areas under the curve to really represent probabilities of seeing things. So going back to the normal distribution, the 68, 95, 99.7 rule tells me this. Roughly 68% of my data falls between one standard deviation of the mean. So plus or minus a standard deviation should give me about 68%. Plus or minus 2 gives me approximately 95. Plus or minus 3 gives me approximately 99.7. So that's why when we take a look at those key values for z, the plus and minus 2 are big things for us because 95% fall within 2 which means that if you fall outside here to the right, there's a total of 5% on the outside, 2.5 on each side. So you're sitting in the most extreme 2.5% of the distribution. While not possible to see, it just becomes pretty unlikely for us to see. So this is the normal distribution right here. Those are the exact probabilities based on the normal distribution. Again, this is a probability density function. Here's that density function. This is the function we use to graph it. We don't need to be too concerned with that. But one of the things we do need to know is that there are an infinite number of normal distributions. All depends on a mean and a standard deviation. And then it just kind of gets plugged into this and gives us that form. Now, what ends up happening is by converting them to z-scores and by converting things in a normal distribution to z-scores, we create a distribution with a mean of 0 and a standard deviation of 1. So what happens is we take an infinite number of normal distributions and we bring it down into just a single one. And what happens there is it really helps us identify areas under the curve, because those aren't easy to find. It's not a well-defined shape, and it's a very complex function. So we create what they call a z-table. And that's what we've been taking a look at the last couple of weeks, the z-table right here. And what a z-table says is, if I'm looking at a normal distribution with a mean of 0 and a standard deviation of 1, this is the area under the curve to the left of a z-value that we happen to see. So I've got my z-values left-hand side. I see the first 2 digits. The top part gives me that last digit. And then I can find the area under the curve to the left within this table. So there's positive, negative side. This table right here tells me area under the curve to the left. Okay, so let's do a couple of examples. Find the area to the left of the following z-values. Area to the left. Z equals negative 0.6. Okay, so if I want to find the area to the left under the curve of a z-value, I come to this table and I just look at it. Negative 0.6. I'm going to come down the left-hand side here, scroll down till I see negative 0.6. I see it right here. And then I'm going to use that first column because there is not another digit. That's the same as 0.60. So I come down and I see that that value becomes 0.2743. So the area to the left under the normal curve of negative 0.6 is 0.2743. And that's how we do that. Now let's find the area to the left under the curve for z equals 1.5. So I'm going to do the same thing. I'm going to come here. I'm going to come to this positive version of the table. And I'm going to look this value up 1.5. Come here, same thing, 1.50. I get 0.9332. So my key value here, my area to the left will be 0.9332. And that's how we find areas to the left. That's the easiest of all. Questions on that? So to find the area to the left, just look up the value on the table. All right. Now let's talk about finding areas to the right. Now, the table we have tells me areas to the left. So let's pull this up on the board here, take a look, see what we got. So if I have my normal distribution here, and I look up a value z, on this table, what's going to happen is I'm going to end up finding the area to the left. This is from the table that we see. Now, if I want to find the area to the right, we just need to remember that the total area under the curve is equal to 1. So this plus this has to equal 1. Therefore, this becomes 1 minus the area to the left. So that's what I'm trying to do. I'm going to look up the value on the table, find that as the area to the left, and then I'm going to subtract it from 1. And that's going to give me the area to the right. So let's take a look at doing some of those values here. All right, let's find the area to the right of z equals 2.3. All right, so what I'm going to do is I'm going to come to the table, and the first thing I'm going to do for this one right here is say, what's the area to the left? I'm going to take a look at that value, 2.3. 2.3 gives me 0.9893. 0.9893, that's the area to the left. And then what I'm going to do is I'm going to subtract that from 1. And so the area to the right is going to be 1 minus 0.989. We do that calculation, we get 0.1017. And so that's how we find areas to the right. And then we'll do the same thing with negative 1.25, find the area to the right. First thing we want to do, though, is we want to look up the area to the left. Negative 1.25. I'm going to come over here. This is the first one we've had that second digit. So I'm going to come down here on the left, look up negative 1.2. And then I'm going to come over to the 0.05 column right here. Negative 1.25, 0.1056. So that's the area to the left, 0.1056. Once I have the area to the left, I can find the area to the right by just subtracting it from 1. So I do that math right there. I get 0.8944. All right, any questions so far finding areas to the left or areas to the right? All right, so in general, to find the area to the right will be found by taking 1 minus the area to the left. And then the table tells me what the area to the left is. Last one's talking about finding the area between two z values. If I want to find the area between two z values, what I'm going to do is I'm going to find the area to the left of both of them. I'm going to find the area to the left of negative 1.25 in this case. And I'm going to find the area to the left of 0.75. So area to the left of negative 1.25, we actually just looked that one up, 0.1056. Now we got to find the area to the left of 0.75. So I'm going to come back to my table here, 0.75. And I see that I get a score of 0.7734. So that value is 0.7734. To find the area between, I'm going to subtract the smaller amount from the bigger amount. So that's going to give me 0.7734 minus 0.1056. I do that math. And I get a value of, if I can find this calculator here, 0.6678. And that's how we find the area between. Next one, between -1 and 0.85. I find the area to the left of each one. And then I subtract the smaller from the bigger. And that's how I get it. So I just have to look up those two numbers on the table. -1 becomes 0.1587. And then 0.85, 0.8 over to 0.05, I get 0.8023. And then I just subtract the smaller number from the bigger number. And then I get my answer on the back end. .6436. And that's how we do that, finding areas between. So area between, find both areas to the left, subtract the biggest number minus the smaller number, and that'll give you the area between. It should not be greater than 1, and it should not be negative. All right. Questions on reading that Z table, understanding what we're doing. Okay. So when we're dealing with those things right there, really we can take a look at areas to the left as probabilities of seeing something like that or less. We can take a look at areas to the right being the probability of something like that or larger. And then areas between, that would be the probability that something falls between two values. So let's go back up to that previous problem I was talking about and say, okay, exam scores follow a normal distribution with a mean of 70 and a standard deviation of 12. Which exam represents the 90th percentile of exam scores? So in order to answer this, we have to remember what a percentile represents. So if you're in the 90th percentile, that means that 90% of the data falls below you. If you're in the 60th, 60% of the data falls. If you're in the 30th, 30% falls below you. Whatever percent you are, that's how much data falls below you. So if I was curious as what the 90th percentile of exam scores that come from a normal distribution, I would come to my Z table and I would try and find the point such that 90% of the data was less than. So if I take a look here, I'm going to look in this middle. This is kind of what we were doing when we were finding those critical Z values this week. Try and find 0.90, and I don't see it exactly, but I do see 0.8997. That's pretty close, right? Next one jumps over a little bit. Value's pretty close to 1.28. So the 90th percentile is approximately a Z-score of 1.28. So we would come back here and we would basically just say 90th percentile represented by Z equals 1.28. And then we would use this equation we just had here to find out what that measurement value was. So we plug that into our calculator and we get 85.36. All right, any questions so far? All right. So that was most of the stuff we were taking a look at through chapter 3. Now we get into chapter 4, and we really start talking about the beginning of inferential statistics. So we started talking about sampling distributions. So a sampling distribution is the probability distribution that shows up when we collect samples repeatedly of the same size from some population. So what that would mean is, let's take a look at our class as example. So there's 35 students in each class. If I sampled 5 students at a time and measured their exam score and find out what the average was, I would end up with a bunch of different possibilities for sample means. And so the collection of all those would create a distribution of themselves. So that's the concept. It's basically a distribution of a sample that comes from some population. If I'm dealing with a sample mean, a couple of things happen. The expected value, or the mean of all the samples, should be approximately equal to the population. And if I collect data over everything, it will be exactly the population. My prediction gets better and better as my sample size increases, and then the variability within my prediction goes down. Well, for example, right, if I have 35 of you in the class, if I take a sample of size 5, well, my estimate for the mean may not be that good, might be off by it. But if I collect 15 of you, well, it's going to get closer to the actual value of the mean. 25 of you, I'm going to get even closer to the value. If I had 30 of you, I'm going to get even closer. So as my sample size increases, so does my estimate of the sample mean for the population. That's the concept there. And that brings us into the central limit theorem, which says that if my sample size is sufficiently large, meaning that the n is greater than or equal to 30, or maybe a little bit larger for some different types of distributions, then the distribution of the sample mean is approximately a normal distribution. And that's what allows us to do a lot of these statistical analysis that we do in this class, is because we can use that Z table and the T table going forward, because we can make the assumption that it's a normal distribution. And so what happens is, if I want to compute probabilities with the central limit theorem, I can compute a Z value, which is equivalent to X bar minus mu over sigma over the square root of n. So it's really the same Z value. The only thing that's changing is our standard deviation is changed to sigma over the square root of n. And then instead of looking at a single value, I'm looking at the mean of several values. So then we end up seeing something like this. So let's take a look at an example. All right, the local brewery fills their beer bottles using a process that follows a normal distribution with a mean of 12 fluid ounces and a standard deviation of 0.6 fluid ounces. We decide to buy 3 12-packs, which are 36 total beers, and measure the contents of each one. We find the mean of our sample to be 11.8 fluid ounces. Let's find the Z value and the area to the left under the normal distribution curve. Okay, so a couple of things I want to note when I'm reading this. I see that I understand that I'm looking at beer bottles from the local brewery. That's my population. And that's going to follow a normal distribution, which tells me I'm probably going to use Z or T. All right, the mean of that population is 12 and the standard deviation is 0.6. In this case, I know information about the population, so I'm going to end up using my Z statistic when it comes to this problem. So I get Z is something I'm going to use, and I note that I'm dealing with more than a single value. That probably tells me I'm looking at this mean version of my Z score right here. So then I just need to identify which numbers in the words represent which symbols that I'm taking a look at. When I'm coming through here, taking a look, X bar is my sample mean, mu is my population. Sigma, population standard deviation. N is the sample size. So my sample mean, we find the mean of our sample to be 11.8. That would be the sample mean. When we take a look at the local brewery fills their beer bottles using a process that follows a normal distribution with the mean of the process, that's the mean of the population here, that's going to be 12. Sigma, there's only one standard deviation given to us. Standard deviation is 0.6. And then my square root of n, I just plug in square root of n, and it's 36. So then I plug this into my calculator, and I see what I get. So on the top, 11.8 minus 12, that gives me negative 0.2. And I'm going to divide that by 0.6 divided by the square root of 36. Square root of 36 is just 6. So I do a little bit more math. Negative 0.2 divided by 0.1, which is equal to negative 2. So my z-score here is negative 2. Now the problem says find the z-value and the area to the left under the normal distribution curve. Area to the left of z equals 2. I'm going to come back to my z table and I'm going to look it up. Negative 2.0228. So the area to the left is 0.0228. And I've done that problem. This is a negative 2. And that's how we do that. Questions on that? Okay, so that's some of the key stuff there. I just wanted to remind us how to find critical t-values, because when we got to the critical z-values, the critical z-values were always the same, right? If it's an 80% confidence interval, it's 1.282, 90% 1.645, 95% 1.96, etc. We can just have those written down and memorized. But the critical t-values take us a little bit of time. We have to look it up every single time we do a problem. So here's the process going forward. I take my confidence level percentage, turn it into a decimal, and subtract it from 1. I divide it by 2, and that gives me my alpha value on top of the t-table. So I've got my t-table, alpha values across the top. And then I need to find my degrees of freedom, because my degrees of freedom come here down that left-hand side. So in this case, I have a sample size of 12. My degrees of freedom is n minus 1, 11 degrees of freedom. So I'm going to go to my table. I'm going to go to new equals 11 on the left-hand side and go to alpha equals 0.05. That's going to be the second column here. Come down to 11 degrees of freedom. And I see that it has a critical t-value here of 1.796. So that's the process we go through when we're trying to find those critical t-values. Now, we can go through this process every time. 95%, 0.95 is the area, subtracted from 1 divided by 2. Or we might be able to just take this t-table and write down some information here. Like this first column right here, this is an 80% confidence interval critical t-value. So the first one represents an 80% confidence interval. Next one is a 90% confidence interval. Then a 95%. Then a 98%. Then a 99%. That's probably as far as we need to go. So if I have that memorized, I can just say up 90%, go to the second column. I've got my value right there. And then just a reminder at the very bottom, where we have that infinity symbol, this represents the critical z value for each one of those right there. So that might help guide me to make sure I know which value I'm looking at. I know that the 90% Z value is 1.645, I know I have to use this column. So that can help. All right, any questions about finding those critical T values? So we're going to learn it we learned it for confidence intervals. We'll talk about how we do with it with the next class. There's just a slight fluctuation in how we compute alpha for hypothesis tests. Okay, get this back to normal here. Example, should we use Z or T? This is where we would come the question of, am I computing a critical Z value, critical T value, which distribution am I using? So example 1, a winemaker produces a special bottle of Pinot Noir each year, and their process provides an alcohol content that follows a normal distribution with a mean of 14% and a standard deviation of 3%. We sample 25 bottles and see there is an average of 13% alcohol by volume. All right, so the question is, do I use a Z distribution or do I use a T distribution? Does anyone want to venture a guess at that? So it's not going to be a T, and we'll talk about why. This is why I wanted to bring examples like this up. So we have to understand what the values we see in the problem, what do they represent and what do they relate to? So if we take a look at this, we say the winemaker produces a bottle and their process provides something that follows a normal distribution with a mean and a standard deviation, right? So this information is related to the population of all Pinot Noir bottles that are made from this winemaker. The sample we're taking a look at is just the 25 bottles, which has a different mean, 13%. And then I didn't give you a standard deviation that was related with the sample. So we just need to try and read the problem, because sometimes it's not going to be as cut and dry as the population standard deviation is blank, right? Sometimes it's just going to be words like this, and we're going to have to parse out what do those values relate to. Normally we'll see the word a sample of this with a mean or standard deviation of that. They'll be clustered together. So the first answer here, we want to use a Z distribution because we know the population standard deviation. All right, next one. Crumble Cookies claim their cookies weigh 5.5 ounces on average. We sample 25 cookies and find the average weight to be 6 ounces with a standard deviation of 1.2 ounces. All right, question here, are we going to use Z or are we going to use T? So taking a look at this one, we have to read and understand which values are represented or are related to which quantities here. So Crumble claims their cookies weigh 5.5 ounces on average. This right here is a population mean, right? How did I find this problem? I went to their app and I looked up the weights, 5.5 ounces. That's the average weight right there. It did not report a standard deviation. So we collected a sample of 25 cookies. We found that the average weight of those cookies was actually 6 ounces, and the standard deviation was 1.2 ounces. These are all related to the sample. So the only information I have here is the sample standard deviation. So I want to use T because I do not know the population standard deviation. The only thing I know is the population mean. That's what we have there. All right, questions on choosing Z or T. We just have to be a little bit careful when it comes to reading those words and seeing which values are related to which. That's why I wanted to put an example like this up there. And we'll see some more going forward. We'll see another one coming up in a couple slides. All right, any questions about that? Okay. So then, just wanted to reiterate the confidence interval thing here. So when we're trying to find confidence intervals for the mean, what we do is we basically just take this concept right here. I'm going to take the sample mean, and I'm going to add and subtract the margin of error. The margin of error will look very similar to this, whether I'm using Z or T. If I am using T, I have to look up that critical T value like we just did a little bit ago, and then compute S, and I can compute it as T critical times S over the square root of N. If it's Z, this just becomes Z critical, and this becomes sigma. Otherwise, it's the exact same calculation. So that's the concept right there. Okay, so let's do one real quick to make sure we can compute a confidence interval. I'm calculating how long students spend doing their homework in my PSY 230 each week. I sample my class of 35 students and find the average to be 6.5 hours with a standard deviation of 4 hours. Find the 90% confidence interval for average time studied. Okay, so we're going to get one more crack at it. I take a look at this problem right here. It doesn't say that it follows a normal distribution, but my sample size is big enough. Sample size is big enough. I don't want to be careful. I want to change this number to 31. We'll talk about why in a second. Okay, am I going to use Z or T when it comes to this problem? Z or T? So I'm seeing a couple of Z's. What makes you think we're going to use Z? Okay, so the real key indicator between should we use Z or T is we should determine whether or not I know the population standard deviation or not. So do I know the population standard deviation or not? This is definitely a slightly tricky problem here, right? Am I just looking at one class? Or am I looking at students spend doing homework in PSY 230 each week? So this really comes down to understanding what that population of interest actually is. And I realize as I'm taking a look at this, maybe the problem's not crystal clear on what that population of interest is, right? So if I take a look at this, I'm sampling my class. If I'm only interested in my single class of 31 students, then I would actually have a census, right? I would have everything in a population. But I have to be more clear about that. So let me be more clear on the problem. My apologies, I wrote this a little bit late and I wasn't quite as clear. Calculating how long students spend doing their homework in all PSY 230 classes each week. I sample my class of 31 students and find the average to be 6.5 hours with a standard deviation of 4 hours. Find the 90% confidence interval for the average time studied. Now, by clarifying that the population are all PSY 230 students, am I going to use a Z or a T in this case? The answer will be T, right? And I'm going to use a T distribution because I do not know the population standard deviation. I'm calculating the sample of my 31 students. Standard deviation is 4 hours. So I'm going to use a T distribution here. And the concept of the T distribution is I need to find the margin of error, which means I need to go look up this critical T value right here. 90% confidence interval, sample size is 31. So I'm going to go back to my T table. 90% is this second column right here. 31 minus 1, that's 30 degrees of freedom. 1.697 is that critical T value, 1.697. So critical T value is 1.697. I'm going to multiply that by S, which is 4, divided by the square roots of my sample size, which is 31. And then I have to plug this into my calculator and see what I happen to get. So I get a margin of error of 1.219. We'll round that to 1.22. All right, once I have my margin of error, I can find my left endpoint and my right endpoints by taking the mean, subtracting E, taking the mean, adding E. So I'm going to take the mean. My sample mean was 6.5. I'm going to subtract 1.22. My sample mean 6.5. I'm going to add 1.22. It's going to give me my lower and my upper bounds here. This should be 6.28, sorry, 5.28. And this one should be 7.72. So then I would write out my confidence intervals 5.28, 7.72, and then I have my 90% confidence interval for how long students spend studying for PSY 230 on average. All right, so what would have changed if I didn't make that one adjustment to this problem, if I didn't clear it up? If I was actually dealing with the population, what is the one thing that would have changed in this problem?
Can you repeat that? Sorry.
Yeah, no worries. So if I didn't make this change here, how long students spend in my PSY 230 class each week. So if I left this as it initially was, where it looked like we were collecting a census, what would be the difference in this problem going forward?
Would it be the difference between using either the T or the Z?
That's exactly right. So instead of using T, we would have used Z. And the only thing that would have changed in the problem is this value right here. This value right here. Instead of using T critical, we would have used the Z critical value for the 90%, which would have been 1.645. So that's really the only thing that changes in the problems between Z and T, is that critical T value right there. Critical T versus critical T. All right. All right, that's it. That's all I've got. I hope that was where someone stopped recording for now.